Okay, we're just going to get started. If you could take your seats. And I'd just like to make a couple of announcements before we get started with the last session of the day. So the first is that there have been a lot of questions during the meeting, which has been fantastic. If you do have a question, please wait for the microphone. It helps people to hear, but it also helps with some video recording that we're doing. We're hoping to make video recordings of the talks available later. So if we want to be able to capture that audio, it's really important that you speak into the microphone. The other quick announcement I wanted to make is about the lab tours that we're organizing during the poster session. So they're running concurrent with the poster session on Wednesday. We sent out a request to just ask who was interested in attending those lab tours, but I want to get a sense of whether we have accurate information. So if you're interested in attending the lab tours, could you raise your hand? So Stephen, you said something. Okay, so if you, can you keep your hands up? So if you are interested in attending the lab tours and you signed up to go to the lab tours, could you lower your hand? Okay, good. Okay, so just a few. Okay. No shame, really, I know. But it's helpful for us to know how many slots to add. So it sounds like maybe we should add 10 slots or so on the lab tours, I would say. Okay. All right, so thanks. So I'll hand things back over to you, Kai, who is moderating the session.
All right, so our next speaker will be Mark Zhandry, who will talk about quantum query solvability, a refinement of quantum query complexity and applications.
Hi, everyone. So this is going to be a very high-level talk about basically the way that I would prefer to see quantum query results stated, which has slightly more information than quantum query complexity. And it turns out that this little bit of extra information is very useful, especially in cryptography, which is really what I do. So let's just get right into it. So quantum query complexity is roughly a question of how many quantum queries are required to solve a given oracle task. So you have some oracle, and you're allowed to query it on quantum superpositions, and your goal is to find out some information about the oracle. So for example, here we have pre-image search, where we have some function on domain size m, range size n. We can query it on quantum superpositions of inputs, and we get the superpositions of outputs back, properly encoded to make this whole thing unitary. And additionally, the algorithm, which I've represented as an adversary here, because as a cryptographer, we always think of everyone else as an adversary. He also gets an input y, he also gets an element y in the codomain of this function f, and he's supposed to find a pre-image. So an element x in the domain such that f of x equals y. And now we know the Grover's algorithm basically is a statement that this problem can be solved using n to the 1/2 queries. And we know that that's tight. So the quantum query complexity of pre-image search is theta of n to the 1/2. So generally, quantum query complexity results have a form where they state that theta, order of f of some function of the domain size and range size, maybe other parameters as well. Quantum queries are required to solve a given problem with some success probability, say 2/3. And if we, some statements aren't thetas, they're just big O's, which is an upper bound. It says, at most this many queries are required. That's an algorithm. And when you have omegas, that's a lower bound, says at least this many is required. Just some notes. Generally, these existing quantum query complexity results are worst case. They're generally asymptotic in the number of queries, in the sense that if you have a matching upper and lower bound, there's usually at least a constant gap between them. It's very unusual to have an exact number of quantum queries that are required. We almost always allow some errors. We don't normally ask for probability 1 solving the problem. And then this constant 2/3 and the success probability is somewhat arbitrary. You can really pick any constant you want, because you can always just repeat to boost the success probability. And the repetitions, as long as the, whatever you replace 2/3 with is a constant, the repetitions just get absorbed by the big O notation. All right. Cryptographers, they generally want things a little different than what quantum complexity people show. So cryptographers were pretty much always interested in average case. And this is because we don't want it to be that, oh, I can prove for some key that I have that you can't break into my computer. No, I want for most keys I have, a randomly chosen key I have, you can't break into my computer. So we really want average case results. Whereas quantum lower bounds generally rule out algorithms that succeed with high probability, in crypto we really want to even rule out adversaries that succeed with pretty low probability. So if someone is able to break into my bank account with probability 1 over 100, that is horrible. I really want it to be like 1 over trillion or something like that probability, something, or even smaller, something very tiny. In some cases in crypto, we actually want to be a little more precise on the number of queries. It's more of, rather than saying how many queries are required to solve a problem, we want the adversary, we're given him a certain number of queries, and we want to argue that he can't succeed with even pretty small probability. And I'll make this distinction a little more clear later in the talk. And then just another thing I want to point out is that oftentimes the actual problems that are considered are different. And we'll see an example of that today too. The first and the last one are not really the focus of my talk though. I really want to focus on these middle two. So the fact that the success probability we want are different, and also this issue of the asymptotic nature of the number of queries. Okay, so the ideal format of results for crypto is what I'm calling quantum query solvability to distinguish it from quantum query complexity. And it says that given, and the statements of this form would be, given some precise number of quantum queries, let's estimate the maximum success probability. Here we're generally okay with big thetas in the success probability, but we want the queries to be exact. Just some notes, again, are asymptotic in the success probability, not the number of queries. And also, statements of this form make sense even if you want to consider extremely small success probabilities. Whereas in quantum query complexity results, they don't really say anything about that regime. So I'm not trying to suggest that these results aren't out there. There are definitely results of this form in the literature, but for the most part, most of the big statements that have been made are in the quantum query complexity side, where you just sort of set the probability to be 2/3 or whatever constant. Okay, so I want to give you guys a little quiz. So we already said that the quantum query complexity of pre-image search is order of n to the 1/2, where n is the size of the codomain. Here I have a list of possible quantum query solvabilities. So Q is the number of queries you get. What is the right asymptotic bound on the success probability? Show of hands, how many think it's A? B? C? Okay, a few more on C. D? E? Okay. So actually, first we can immediately throw out B and D, because we see that these are inconsistent with the quantum query complexity result. So for example, on B, actually let's do D. So on D, if I set Q to be the required n to the 1/2 to get probability 1 that we know is sufficient, I actually get theta of 1 over n. But we know that we can get a constant, so D is clearly not right. And similarly, B gives you the wrong answer too. A, C, and E, however, if we set theta to be n to the 1/2, we get that the solvability, the probability of success, is actually a constant. So these are so far all consistent with the statement that the quantum query complexity is n to the 1/2. It turns out that the right answer was C. So of those of you who raised your hand, the majority did get it right. But just given the quantum query complexity result, you can't really distinguish between A, C, and E. And I'm not sure if anyone's actually formally proved this, but it's not too hard to show. Yeah.
So, I mean, in the case where there's one solution, isn't there an exact a zero error algorithm?
I believe so. I'm sort of not. I'm placing constraints, or I'm lying to you a little bit here. On, for example, if m is much smaller than n, the domain size is much smaller than the range size. This isn't true anymore. It's not completely accurate what I'm saying, but it's close. Yeah.
So Mark, if I'm not mistaken, that statement that the success probability is q squared over n is in the original BBBV paper from '94.
It might be. Yeah.
I think it is. Yeah.
Okay.
But I was going to say that people the place where people really phrase things the way you're asking for is like when they prove direct product theorems, right? Then it's always phrased in exact because there you are dealing with tiny success probabilities.
Right. Right.
Yeah.
All right, so let's move on to another example problem. This is quantum collision finding. So here, we're still given a function f on domain size m, range size n, still allowed quantum queries, but now my goal is not to find a preimage of a given point, but rather to find a collision. So this is two elements in the domain that map to the same output. And the question of how many quantum queries are needed to find a collision is actually a very interesting one. It has relation to many other problems. Algorithms or lower bounds can imply things for other questions. And collision-resistant functions themselves are very central object to crypto. So collision-resistant function means a function where it's hard to find a collision. So in crypto, we often model functions that are collision resistant as random functions. This is called the random oracle model. It's a very useful model that we have in crypto. One other note that I want to make though is for crypto, we generally want the output of the function to be much smaller than the input. So we want the input to actually be compressing. And in this case, collisions are guaranteed to exist. And we want it to be such that even though collisions are guaranteed to exist, you still can't find any. And quantum query complexity or solvability of the collision finding problem is a useful tool. I mean, it's useful, it's interesting just to know what the answer is, but it's also a useful tool for guiding parameter settings. And I'll talk about that a little more in a couple slides. But first I want to have a little quiz again on so we know that the quantum query complexity of the collision finding problem is n to the 1/3. This is a sequence of results starting in the late 90s. And now given this, what is the quantum query solvability? So any takers on A, B, C, D, E? All right. Looks like most of you got the right answer. Most of you who actually voted got the right answer. So C we can immediately throw out because it's also inconsistent with the quantum query complexity. You can see this just by plugging Q equals n to the 1/3. But the rest of these are all actually consistent just with the statement of quantum query complexity. But the right answer is D. It's Q cubed over n. Okay, so at this point, I want to address the question of who really cares. Do we really care if it's Q over n to the 1/3, which was option A, or Q cubed over n? And I want to argue that yes, we do care. It's an interesting question, first of all. And another sort of point is that it actually may affect practice in the sense that the exact solvability effects could affect the concrete parameters used for cryptographic hash functions. So for example, let's suppose that as sort of an upper bound on the computational power of an adversary, we say, okay, he's not going to be able to make more than 2 to the 80 queries to our hash function. And also, let's consider our hash function broken if with some probability noticeably greater than 2 to the minus 80, he's able to find a collision. Right, so this sort of captures the fact that we're computationally bounding the adversary, and we also want to rule out adversaries even with low success probability. We want to make sure the success probability is extremely low. In the right answer case, Q cubed over n, we see that we need to set the number of elements in the range to be 2 to the 320, which corresponds to 320-bit outputs. In the wrong case, option A, we actually see that we have the required number of output bits is actually 50% more. And so if you're storing hashes like user passwords or movies, whatever have you, there's a 50% change in storage requirements here. And this can, that's a pretty big difference. And then the other point, and the one I really want to drive home today, and we will see an example of this, is that understanding the quantum query solvability in this format actually is useful for proving quantum query complexity results, even if you don't care at all about the quantum query solvability. Okay, and the example of where this is useful is actually a particular case of the quantum collision finding problem. Okay, so I want to talk a little bit now about, give some background on the quantum collision finding problem. So initial results in this space actually proved, initial lower bounds I should say, actually proved lower bounds for an easier problem. And I don't mean to suggest that their task was easier. I mean the problem that they were considering and proving was hard is an easier problem. So that actually means that these results were stronger. And the problem is actually collision detection. Not finding a collision, but just even detecting if one exists. So basically, the adversary is given oracle access to functions from one of two worlds. In one case, he's given a function with many collisions. In the other case, he's given a function with no collisions, totally injective. And his goal is to figure out which is the case. All right, and the early results showed that basically a lower bound of n to the 1/3 for this problem. In the worst case, when the output size is at least as large as the input, this makes sense because when the function is compressing, there has to be collision, so it's not really an interesting problem. And as a direct corollary of lower bounds on the collision detection problem, you get lower bounds on the collision finding problem. Basically, because injective functions have no collisions, if you have a collision finder, you can use it to, the fact that you found a collision automatically says that you're not in the injective case. So you get a distinguisher. Okay, so some notes. As I said before, when the function is compressing, you're guaranteed to have collisions, so the detection problem is actually easy. So the lower bounds on the collision finding problem obtained through this method all have this restriction that the output is no smaller than the input. And actually the very first lower bounds, it was even had a stronger restriction that the output had to be some small amount larger than the input. And then also these results are worst case. They only apply to very uniform functions where every element has the exact same number of pre-images. Okay, but in crypto we want average case, and as I also said earlier on, we want to consider the collision problem for functions that are very, very compressing, because that is the interesting case in crypto. So first I just want to define the average case quantum collision detection problem, and this is the problem of basically distinguishing a random function from a random injective function. All right. Okay, so it turns out that we can extend the lower bounds to the average case problem. Henry Yuan, a couple years ago, or last year I guess, proved n to the 1/5 lower bound using the adversary method in combination with the existing worst case lower bounds. And then I was able to improve this to the optimal n to the 1/3 using some polynomial-like method from a paper of mine a couple years ago. Okay, but these are still lower bounds on the quantum query complexity of the detection problem. But we're interested in the collision problem. So what do? I mean, this automatically gives us a lower bound for the collision problem in the case where the function's not compressing. But again, we want the compressing case. So the actual route to get to this, to get to the case where the function is compressing, is to actually look at the quantum query solvability of this problem. So in my work, I actually show something stronger. I actually show that the quantum query solvability of the detection problem is q cubed over n, as expected. And this gives us an immediate low, bound on the success probability for the average case collision finding problem, again, subject to the restriction that the functions aren't shrinking. So it doesn't seem like I've really done much. I've just, given more refined statements, but I still have this annoying restriction that the functions aren't compressing. So what do I do? Well, it turns out that by looking at the collision finding, looking at the quantum query solvability of the finding problem for this restricted case, we can actually very easily get to the right answer of the solvability for arbitrary domain and range sizes. And this step here is very simple, and this is what I'm gonna, basically the most technical part of my talk today. All right, so the Poof idea is basically a reduction, which is what we love to do in crypto. So we're going to take an adversary that can solve the quantum collision finding problem for arbitrary domain and range sizes with some probability p, where p is a function of m and n. And we're going to convert him into another adversary that solves the collision finding problem for the correct domain and range sizes. Basically, we're going to take the range and just blow it up a bit so that it is larger than the domain. And we will get that he succeeds with some other probability p prime. That's a function of m, n, and k. But we can now that we're in the sort of right setting where we actually have a lower bound, we can get a bound on p prime. And hopefully that'll give us a bound on p. So let me actually describe what we do. It's very simple. So our adversary on the bottom is given an oracle access to this f prime function. What he's going to do is he's going to, in his head, run the original adversary with the function f obtained from f prime by just modding by n. So just basically ignoring the k part. And this is easy to do. Any query that the adversary makes, he just forwards to f prime. And when he gets the response, he just mods by n. OK, so it's easy to see that the adversary in his head actually does see a random function f, if f prime is random. And so he will succeed in finding a collision with some probability p. And what our new adversary is going to do is he's just going to output that collision and be done. And it's not hard to show that the probability that this outer adversary succeeds is exactly p over k. And the reason is it's easiest to see if we sort of assume n and k are relatively prime. Basically, then f prime is really just two oracles, one mod n, one mod k, and they're completely independent. The inner adversary sees the mod n one, gives you a collision mod n, and then just with probability 1 over k, that's also a collision mod k. Right, so we've converted our adversary with probability p into one with probability p over k. And now we want to apply our lower bounds on this new adversary. So we just choose k big enough so that the function is expanding. And now we can apply the lower bound, and we get that his success probability p over k is at most q cubed over the new range size, which is n times k. And now what's nice is in this expression, the k's just cancel out, and we're left with that p is at most q cubed over n. And we're done. OK, so using quantum query solvability for the collision detection problem, we can get all the way to a lower bound, or a bound on the success probability for the collision finding problem for all domain and range sizes, which was not possible before just using the quantum query complexity. And now, even if you don't care about quantum query solvability and all you care about is the quantum query complexity of the collision finding problem, the solvability immediately implies the right complexity lower bound. OK, and now I just wanted to highlight that the exact format of the solvability expression is required here. So suppose that we were that the actual solvability was q over n to the 1/3 instead of q cubed over n. This transformation of adversaries works just fine, but when you go through the math, you end up getting a quantum query complexity that looks very different, and in particular, the quantum query complexity you get is meaningless for a small enough n. So really the fact that the solvability, the max success probability, had this q cubed over n form was crucial for extending the result to arbitrary domain and range sizes. All right, so, question?
So it seems to me that even the original collision lower bounds, because they were based on the polynomial method and on symmetrization, they would give you some average case hardness statement, right? So I mean, is the new thing here just that like you can handle arbitrary range size?
Yeah, I mean, I think using the existing the worst case collision lower bounds, you could get some statement for the average case, but I don't think it's going to be optimal.
Okay.
But that aside, even if you don't care about it being optimal, I think the big advantage here is that we can actually go to arbitrary domain and range sizes.
Okay. All right, thanks.
All right, so that's it for quantum, for the collision finding problem. Next, I want to talk about cases where it doesn't even really make sense to talk about the quantum query complexity. And that's the following problem is one example of this, and it's what has been called quantum oracle interrogation. So I have some function with domain size m and range size n as always, and now instead of finding a preimage or finding a collision, I just want to output values of this function. I want to make some number of queries and just output, one input, one output, or 5 inputs, 5 outputs. For some number of k, I want to output that many input-output pairs. And obviously, this is only going to be interesting if the number of queries is less than the number of input-outputs I want. And this question, the reason that I became interested in it is because it actually comes up in some crypto analysis that I was doing. So you can think of a function like this, if it's secret, as basically like a signing algorithm, a digital signing algorithm, and for signing whatever documents you'd like. And suppose some adversary is able to trick me into signing a superposition of documents, or 5 superpositions of documents. Well, that adversary can, there's nothing I can do at that point. He can just measure his superposition of documents and corresponding signatures, and he'll have 5 signed documents. But what I might hope is that he can't find a 6th signed document if he's only tricked me to sign 5 superpositions. For the crypto application, we usually think of n as being exponential. So like 2 to the 128, 2 to the 256, something like that. And we want that even if he's able to trick me into digitally signing 5 superpositions, he can't come up with 6 signatures. So we want that the success probability is extremely low, even in the case where the number of queries is even just 1 less than the number of outputs he's trying to produce. And the trivial thing to note is that if he's actually able to make a number of queries equal to the number of input-output pairs he's trying to produce, he can actually do this trivially just using classical queries. He can just query the function on k inputs. So what we really want is a sharp threshold between k-1 queries and k queries. And so an asymptotic query count here is really meaningless, right? Even a factor of 2 is too much. We'd really want an additive, just constant 1. So if you had some asymptotic thing saying theta of n, or theta of k queries are required, it doesn't really say anything for us in crypto. So the main prior work on this was in the late 90s, where it was shown that you can, in the special case where the output of this function is just a single bit, you can actually save a factor of 2, and you only have to do slightly over half of k queries to output k input-output pairs with overwhelming probability. And then this looks very troubling for us because, as we said, even a factor of 2 kills us. But hopefully the fact that we want n to be, we're going to have functions where n is exponential will save us, because this only applies to n equals 2. Okay, so the sort of starting point is to see how the Van Dam result generalizes to arbitrary range sizes n. And to do this, basically, if you open up the analysis, you actually see that the success probability in the algorithm for the n equals 2 case is this funny sum of binomials. And the way it sort of naturally generalizes to arbitrary n, and you get this funny expression where it's the sum of binomials plus a power of times a power of n minus 1. And you see that if we set n equals 2, we recover the original probability. Okay, so analyzing this thing, if we set n to be some small constant, it turns out that you can set q, the number of queries, to be some constant fraction of the number of outputs you want, and you can get success probability very close to 1. For example, if n equals 4, which corresponds to a function that just outputs 2 bits, we only need 3/4 k queries roughly to output k points. Okay, but fortunately for us, this algorithm just doesn't work anymore when we set k to be very large. When we set k to be some exponential function in q, even when q is 1 less than k, we get a very tiny success probability. So that's good news. This factor of 2 does not generalize to arbitrary n. But the obvious question is this tight? You know, it's just, we just generalized one algorithm. Maybe there's another. All right, so, you know, I spent a while trying to come up with a lower bound for this. I wanted to show this algorithm was tight. But existing methods didn't really seem to cut it as is, or at least my understanding of them wasn't sufficient enough to use them. And the problem for me, or one of the problems for me, was that the theorem statements were always asymptotic in the query number. And as we said here, asymptotic in the query number is meaningless because even a factor of 2 kills us. If it's asymptotic in the success probability, that's okay. You know, if some tiny probability times a constant is still pretty tiny. So we're okay with asymptotics in the success probability, but query number we're not. And the existing methods as is don't really seem to give you that. And there were some other difficulties in using. So my PhD advisor and we developed a new method called the rank, which we called the rank method. And basically what it does is that it's a way to relate success probabilities of a Q query algorithm to a zero query algorithm. Zero queries we can analyze easily, and so it gives you some sort of bound on Q query algorithms. And this method was really built from the start to handle, to really work in this setting where we set the number of queries and then estimate the success probability. And we were able to show that this generalization of Van Dam's algorithm is actually exactly optimal. That this funny expression C is actually the best you can possibly do. So I just want to remark that even though we developed a new method, it apparently wasn't actually necessary. Some other people after us were able to reprove the same result using some generalization of the polynomial method. But the problem for someone in crypto who isn't necessarily an expert in all these existing methods is just that they were hard to use in this setting. One of the reasons being them being asymptotic in the query number. Okay, so the main takeaways from here is this quantum query solvability, I think, is a very natural notion to study. Yes, it means that if a theorem statement bounding the success probability given a number of queries is slightly more complicated because now you have this parameter Q. But I think it's not too complicated. I think we can handle it. I think that quantum query solvability reveals important information that is missed when you just look at the quantum query complexity. And this was demonstrated by the quantum collision case, where the quantum query solvability allowed you to extend to arbitrary range and domain, but complexity did not. This format of results is good for cryptographers. So if you want to make cryptographers happy, try to prove your results in the solvability format. And I guess sort of like maybe an open question is, does this quantum query solvability, maybe it can yield some new insights into the power of a quantum query. So for example, in all of the problems that I talked about today, there was an extra factor of Q in the quantum query solvability. You know, pre-image search went from Q over n to Q squared over n. Collision finding went from Q squared over n to Q cubed over n. And the oracle interrogation went from 1 over n to Q plus 1 over n. And maybe it's just a coincidence that these problems get this extra factor of Q, or maybe there's something deeper going on here. And maybe one of the ways to see if something deeper is going on is to really try to understand quantum query solvability more. All right, and that's all I have. Thank you.
Any questions?
In the examples that you gave, the scaling of the quantum query solvability with n was always inverse, like 1 over n. Do you know of any examples where it's not?
Off the top of my head, no. But I feel like there are, I just can't think of any off the top of my head.
Thanks.
More questions?
Could you explain the last point again? What is this extra Q factor that you're talking about?
So in all three examples, when you look at the classical query solvability, so the classical probability of success given Q queries versus the quantum one is roughly a factor of Q larger than the classical one in all three examples.
Thanks.
More questions? So I have sort of an open-ended question. Are there other query complexity problems motivated by cryptography that you think haven't been studied otherwise? Sort of in the complexity theory literature?
I mean, so one that unfortunately, most recently my work has been in the classical setting, so it's I need to sort of reboot on what sort of quantum problems I was thinking about, and I can't remember any off the top of my head. Sorry.
Any other questions? If not, let's have the next speaker set up, and let's thank Mark again.
Can we take off the microphone?
I think he removed the. Do you have the little thing that?
Oh, okay.
Oh, it's just in the clicker.
Oh, it's
No, it's the thing that. Oh, I'm sorry. Where's it?
inside here.
Oh, I'm sorry.
Ooh, clever.
Okay.
Nice slides.
Yeah, well, I don't know what to do. And display preferences. Do like mirror or something, right? Show mirror. Mirror displays, you have to write, right?
Guess so. I don't have a Mac.
Okay. How's that look? Okay, that's good. Okay, can everyone hear me in the back? Yes, thank you. And then,
Right. Well, so our next speaker is Eddie Farhi, who will talk about a quantum approximate optimization algorithm.
yeah. Does this thing work? No. Okay, it doesn't matter, I guess. Does this thing work? Sort of. Okay, so I'm going to talk about a quantum approximate optimization algorithm. This work I've done with my collaborators, Jeffrey Goldstone and Sam Gutman. And so what I'm interested in, I don't know why it's scanned like that. It's always a little off on the bottom. I'm sorry. What I'm interested in is combinatorial optimization. This is a high-level talk. I'm not going to go into super detail. I hope you can follow me. So here are problems where we have n bits and m clauses. And we have the bits we represent by a string z. These are 0, 1, or 1 and minus 1. It doesn't really matter. And there's a cost function, which is the sum of individual cost functions from m clauses. And each of these acts on a subset of the bits. And it is defined so that it is 1 if it satisfies and 0 if it does not. And I am interested here in maximization, not minimization, which is kind of interesting because often people have gotten used to wanting to find ground states because there's something natural about finding a ground state in a quantum computer, but that's really not a good language for me to use here, as we'll see. And the reason for that is because I'm interested in an approximation ratio. And what the approximation ratio is first we define the maximum of the cost function, where that's very hard to find, but it exists. The maximum of the cost function. It's the maximum of all 2 to the n strings of the cost function. And the approximation ratio is the value of the cost function that your algorithm outputs divided by the maximum. And since I'm interested in this ratio, you see, if we talked about minimum, this really wouldn't work too well if the minimum was 0. So we like talking, when we talk about optimization, approximation ratios, we really want to talk about maximum. Now, what we want to do is we want to make that big. Now, in the last number of years, 10 years or 15 years, have been really interesting results in classical computer science about the difficulties in finding good approximation ratios. And we know, for example, that if you could go improve upon certain algorithms for finding good approximation ratios, that either p would equal np, or in other cases, the unique games conjecture would be false. So there are really interesting theoretical reasons to care about these approximation ratios. But there are other reasons. There's another reason, and that's that I'm interested actually in the world building a quantum computer. And if you build a quantum computer for optimization, finding the absolute best solution may not be what you really want the quantum computer for. You may be very happy with a good approximation ratio. And maybe sometimes they say the best is the enemy of the good. And maybe we've been too obsessed with looking for algorithms that produce the best solution, when we really should just be looking for good solutions. So now I'm going to talk about a quantum algorithm for this, and I would like to give you the ingredients of the quantum algorithm. Well, first of all, we have this cost function. And given the cost function, there's a unitary that depends on an angle gamma, e to the minus I gamma c. Now, the reason gamma only is an angle is because c has integer eigenvalues. So if gamma wraps around beyond 2 pi, this unitary will just repeat on itself. And note that this unitary can be written as a product of M unitaries because each of those C alphas commute. So this thing is actually a product of unitaries, each of which involves the bits in the clause alpha. So this is a product of M unitaries. Now, there is another operator I would like to consider, which is the sum of the sigma x's. Okay? I call that xj stands for sigma x, and I call b the sum of the sigma x's. And now there's a unitary, which is u of b beta. Beta is also an angle because this has eigenvalues. Each of these has eigenvalues 1 and -1. And if you have n of them, you still have integer eigenvalues. So this is now, it can be written e to the minus I beta b as the product over n individual rotations of individual qubits by angle beta. And each of these commutes, also like they do here. And so this is a simple operator to imagine constructing. And the reason I'm writing it out and I'm belaboring this is because I believe these are very easy to make. And I am interested in building a quantum computer. And the fact that these are easy to build, I think, is important for my discussion. The other thing I would like to consider as an ingredient is the state S, which is the uniform superposition over all strings Z. And that's also an easy to construct state. So now I would like to start to discuss how the algorithm could work. So first of all, I would like to have an integer p, which is 1 up to anything. And for each p, I want to define p angles gamma and p angles beta. And I write this collection of angles as a vector. It's just notation. I'm not thinking of this as a vector in a vector space. It's just notation for this collection. And this is, if my script was, I could boldface this if I knew how to do tech or something, but I don't. So I have to put arrows. So that's just what this stands for. So now consider the state gamma beta, which is acting on the state S. First you act with the unitary with C, with angle gamma 1, and then you act with the unitary with B, with beta 1, and then you do it with gamma 2, beta 2, ... So it's a product of these things. Now, note that to construct this state, the required circuit depth is not much because the circuit depth of U of B beta is 1. Because it's a bunch of commuting operators. And the circuit depth of UC gamma is at most P. No, it's at most M, excuse me, it's at most M. And so, but it isn't, it's much less than that if you organize the terms appropriately. But at worst, it's this. So the required circuit depth here is MP plus P. Now, I would like to consider the quantum expectation of the cost function in the state gamma beta. So let's just consider this. All right? If there are any questions, please ask. Okay, we're good? Now, I would like to consider an object which I call M sub p, which is the maximum over gamma and beta of fp gamma beta. You know, C is the cost function, so kind of you can see we want to make a quantum state that makes this big. So imagine, so let me